Okay, everyone, this is Unit 3, the first video tutorial, and we're going to do some of the trickier Lewis structure problems and introducing the concepts of formal charge and resonance. Okay, so the first thing that we want to do is take CO2, which is, as we know, carbon dioxide, and we're going to draw this out. So if you want to try it on your own first, just pause the video, sketch it out, and so on. If not, just follow along. Carbon's least electronegative, it's going to go in the middle. Okay, I'm going to get 4 electrons from carbon, valence of carbon, and I'm going to get 6 times 2 for oxygen. So that's a total of 16 electrons that I have to work with. So if I start filling these in, I'm going to connect, so that's 4 electrons. I'm going to fill in my exterior atoms first. So that's 8, and 8 is 16. So I've already used 16 electrons, but carbon is not happy. So this doesn't work. So there's a couple options on what we can do. We need to share more, for sure. So if I put 2 more in here, in the middle, and make a double bond, that's going to help. So that would be a double bond. I'd still have 4 electrons around the oxygen. Like that. Okay. Carbon is still not quite happy. It needs 2 more. So I'm going to share more. Now I'm going to be symmetrical about this and do a double bond on each side. And there's still 4 electrons around the oxygen. Doesn't really matter where you put them, as long as you show that they're there. Now I've used 16 electrons, and everyone kind of has the illusion that they're happy, right? Everyone thinks they have 8, even though they're sharing a lot. Okay? So this is a valid Lewis structure for carbon dioxide, and this is in fact how we see it in nature. However, some of you may have ended up, instead of sharing that second bond on the right side, you could have shared more on the one side and just had a triple bond. Sorry, the landscapers are driving by. Okay, so you could have had a triple bond here and a single bond here, and that would completely satisfy the rules. So the question becomes, which way does it actually exist in the world? Because both of these structures are legal Lewis structures. We have followed the rules. Everyone's happy. Everyone has 8. We use 16 electrons. So if you are interacting with carbon dioxide in the real world, which we are on a regular basis, which carbon dioxide are we dealing with? The answer is the first one. It's this one. But there's a reason why. And the reason why can be summed up in this concept called formal charge. Okay? This is a made-up number. It's not a real charge. Okay? It's our way of calculating which way the atoms are happiest, right? Because sometimes the atoms like to bond a certain way. So for example, if you look here at the differences, right? In the first example, we'll call this structure 1, this structure 2. In structure 1, the oxygens are bonding with 2 bonds, and then they have 4 electrons on their own. Same on the right. On the bottom structure, structure 2, the oxygen on the left only has 2 electrons of its own, and it has 3 bond with carbon. And then the other one only has 1 bond with carbon, and it has 6 electrons on its own. So the question is there a way we can measure which way oxygen would prefer? And the answer is yes, and that's why we created this thing called formal charge. Okay, so by definition, a formal charge, we'll just say FC, equals, there's a little bit of a formula here, the number of valence electrons, right, minus the number of non-bonding electrons plus 1/2 of the bonded electrons. Okay, and we'll show you kind of what this means in a second. So basically, if you think about it, think of what group oxygen is in, right? So oxygen is in group 6, okay? So what does it want to do? Oxygen's in group 6. It wants to be like neon, if you're looking at your periodic table. It wants 2 more electrons. So in theory, oxygen would want to bond twice. That should make sense. Carbon is in group 4. In theory, carbon should want to bond 4 times, right? And so that would be a perfect scenario. That's where they're happiest. And that's what formal charge does, right? We calculate for each atom in a compound. Okay, you calculate this for each atom in a compound. The ideal situation is all formal charges equal 0. Okay? Or we could say, or the charge on the compound. We'll get to that in a second. Okay? So ideal would be formal charge equals 0 for everybody. If everybody is 0, that's perfect scenario. That's the best structure possible. If there has to be a formal charge, right? If there's no way to get around it, then what we do is we put the negative on the most electronegative atom. Okay? So if there has to be formal charge, things will be more negative, or happier being more negative if they are more electronegative, which hopefully makes sense. So let's use formal charge to address which one of these structures is the best. So let me just redraw these down here. So we have this one, and we have this one. Okay, so we're going to calculate formal charge for each specific atom. So I'm going to say the valence minus, right? So total valence minus number of non-bonding electrons plus half of the bonded electrons. So here we go. Oxygen's valence is what? 6. So I'm going to subtract the number of non-bonding electrons that the oxygen has. So oxygen has 2 here and 2 here. So it has 4 non-bonding electrons. It also has, okay, 4 electrons in bonds. Okay? Now really only one of those we would say would belong to oxygen because they're sharing, right? And so that's why we say half of the bonding electrons, or half of 4, which is 2. Okay? So we end up with 4 plus half of 4, which is 2. So this is 6. 6 minus 6 equals 0. So the formal charge on this oxygen is 0, which is great. Okay, look at carbon now. Okay, carbon, valence of 4 minus non-bonding electrons, 0, there are none, plus half of all of the bonding electrons. So I have 4 here and 4 here, so I have 8. Okay, so 4 minus half of 8 is 4, 0. Perfect. Carbon's formal charge, 0. Now, you can save yourself some time. Look at the oxygen on the right. It is in the same exact scenario as the oxygen on the left, which means our formal charge will be the same, 0, right? I have 4 non-bonding electrons, and then I have 4 bonded electrons, okay? That's why we see carbon dioxide in this version here, right, over here. We see it in this version because all of the formal charges are 0. Look what happens if we do it for the equation on the right. Oxygen's valence is 6, minus its non-bonding electrons, which is 2, plus 1/2 of all of its bonded electrons, which are 6. So 2 plus half of 6 is 5. right? This is all 5. So 6 minus 5, positive 1. So that means this oxygen has a positive 1 formal charge. Carbon, valence of 4, 0 non-bonding, 1/2 of all the bonded, which is 8. 4 minus 4 equals 0. Carbon is 0. Oxygen on the right, valence of 6, minus all of its non-bonding, in this case is 6, plus half of its bonding, right? 1/2 of 2, okay? And so we end up with 7. 6 minus 7 equals -1. -1. Okay? General rule. Total formal charge equals charge on compound. Okay? So carbon dioxide has no charge, therefore its formal charges should all add up to 0. But look what we have here. Right? Not terrible, because we have, like a +1, -1, 0, and so on. Right? They're not huge numbers, but they're not 0. And even though I have a negative over here on this oxygen, I have a positive on this oxygen. Oxygen being the more electronegative, that's not ideal. Right? And so the best case scenario for this one is carbon dioxide. Okay? So best case scenario is no formal charges on anyone, right, unless the compound is charged. Next best scenario is that if you have to have a formal charge, 1, make sure they're small, and 2, put the -1 on the more electronegative atom. Okay, so hopefully that makes some sense. Let's try one more here and see if we can make this work. So let's try this one. This one's a little bit tricky. This is an ion, OCN. Okay, it has a -1 charge overall. Okay, a -1 charge overall. So how do we do that? Well, we're going to write it out like this. Carbon in the middle, least electronegative. Oxygen over here. Nitrogen over here. What's the total valence? Okay, so I'm going to get 6 from oxygen, 4 from carbon, 5 from nitrogen. That should be a red flag to you right there, because we don't like to have odd number electrons. Okay, but I also have a charge. I have a charge of -1 on this compound, which means there is an extra electron in there somewhere. So I'm just going to add in the charge. So that's going to be 16 electrons. Okay, 16 electrons. Connect. Okay, and go from there. That's 16. So we have a similar problem to what we just had with carbon dioxide. So I have to make a legal structure. I have to share more. I have to share a couple of pairs of electrons. One option is that I'm going to share this way. Right? I'm going to throw a pair of electrons from here and from here into the middle. So that's one option. We'll call that structure number 1. Another option would be to keep this one a single bond, but to make this one a triple bond, right? So in other words, sharing more. I still used 16. Everybody's happy. That's option number 2. Option number 3 would be to do that the other way. Right? Oops, sorry. All right, option number 2 would be to do it this way. Right, flip it around, triple bond on the other side. Those are our 3 options. Now, of course, you could put oxygen or nitrogen in the middle potentially, but that's not following the rule of least electronegative in the middle. Okay, so which one is the ideal scenario? Calculate formal charge, right? There's tricks to formal charge. There's shortcuts, okay? And I will tell you that if an atom is doing exactly what it wants to do, formal charge will be 0. What I mean by that is oxygen is in group 6. If it has 2 bonds, oxygen will always have a 0 formal charge. So that's where we have over here. This is oxygen in the perfect scenario. 2 bonds, okay? 4 of its own, 2 bonds. That's perfect oxygen. You can prove it by calculating the formal charge. We just did it up here with CO2. Oxygen with 4 of its own and 2 bonds is perfect. So oxygen here is 0. Okay? Now look at the oxygens in structure 2 and structure 3. They are not in that scenario, so they will not be 0. So we will actually have to do the math on those. How about carbon? Carbon is in group 4. When it has all of its electrons in bonds, meaning 4 bonds, carbon is 0. That would be this one, okay? Carbon is 0. Look at the other carbons. Note that even though they have the triple bond and the single bond on opposite sides, they still have all of their electrons in bonds, which means all of the carbons in this case are going to be 0. Okay? Okay, nitrogen. Nitrogen is in group 5. So what does nitrogen want to do? It wants 3 bonds to get to 8. So nitrogen in a perfect world likes to be bonded 3 times with 2 of its own. So that would be this one. 3 bonds, 2 electrons on its own. So the other 2 nitrogens are not 0. Okay? So note here, we are not going to have an option where all 3 atoms have a 0 formal charge. That's not going to be possible with this scenario. Okay? And so we're going to have to figure out which of these options is best, because technically these all have a -1 overall charge, right? So our formal charge has to be -1 overall. Let's prove it, okay? Let's calculate the formal charge of the nitrogen in the first option. Nitrogen's valence is 5. We're going to subtract the 4 electrons it has non-bonding, right? The 1, 2, 3, 4. And then it has, we want half of its bonded electrons. So it has 4 electrons total in bonds, which means 2 of them are going to be for nitrogen. So this should be 5 minus 6, -1 formal charge. Total formal charge equals the charge on the compound, so we're good to go. Second one. This one. Now we do the oxygen. Valence of 6. Minus the 6 electrons that it has on its own, plus half of what it has bonded. And if it has 1 bond, that means that there's just 1 electron there. 6 minus 7, -1. The oxygen's -1 over here. Down at the bottom, we got to do both the oxygen and the nitrogen. Oxygen, valence 6, minus the 2 it has on its own, plus total of 6 bonded, which means 3. 6 minus 5, +1. Okay? Nitrogen, valence of 5, minus the 6 it has total on its own, plus the 1 from the bond. 5 minus 7 equals -2. Okay? All right. Which option is best? So there's already one that we should knock out, and that is number 3. We should knock this out because the others give us smaller formal charges and or 2 of the atoms are 0 out of the 3. So I would say 3 is definitely not correct. Now the question is it structure 1 or is it structure 2? We must have that -1 in there somewhere, right? Somebody has to be -1. So now we have to choose who. Ideally, you put the negative charge on the more electronegative atom. In that case, oxygen is the more electronegative atom. So this is the best structure for this ion because of that. Okay? So based off of formal charge, we would say that we're most likely going to encounter it this way. And that's how we can use formal charge. So if there's more than one way to draw it and you're not sure, you can use formal charge to help you out. Okay? That's the first part. Second phase of this is something called resonance. This is when you can have more than one possible Lewis structure. Okay? And what ends up happening is, in reality, the electrons move, right, between structures, between the two options, or three options, okay? In reality, the electrons move between the structures and live kind of in between. I'll show you this here in a second. So what that means is the electrons are delocalized, right? Which literally means they're not stuck in a spot, like in a particular bond or on a particular atom. They're sort of free flowing around. So here's an example. Ozone. O3 is ozone. So obviously it's all oxygen, so oxygen in the middle, oxygen's on the outside, okay? Oxygen's valence is 6. 6 times 3 is 18 total electrons to work with. Filling them in. I used 16. There's the 18. Someone's not happy, okay? So we got to share more. Where are we going to share? Well, I can take 2 from this side and dump them in, or I can take 2 from this side and dump them in. Doesn't matter, right? In theory, it's the same thing. So what I'm going to do is go like this. Right? But I'm going to put this in brackets and say that there is another possibility. You must represent all possibilities. Okay? I could do it this way as well. Now you might be saying, but isn't that the same thing? It's just flipped 180 degrees. And the answer is no, because what we actually see is some weird form of in-between. We can actually measure the length of these bonds, right? And what we know is single bonds are longer than double bonds. That's just a fact. And when we do more three-dimensional stuff, we'll see why. Single bonds are the longest, then double bonds, and then triple bonds are the shortest. So what we should see is one small bond, right? We'll call that the X bond, and one long bond. We'll call that the Y bond. Or same thing over here. It should be Y, then X, right? At any rate, we should see one bond short, one bond long. What we find, okay, is that if you look at ozone and you actually measure the bonds, you get 2 equal-sized bonds, but it's a distance that's like in between a double bond and a single bond, right? And so it's like this weird in-between where we don't really have a single bond or a double bond. We actually have like 2 1.5 bonds, which is super weird. And so what ends up happening is if I go back to my original like beginning here, okay, what ends up happening if I just take one of these is that this double bond actually sort of floats and flips back and forth and back and forth and back and forth, and these guys kind of flip back and forth, back and forth, back and forth. And it does it so fast. I'm just going to leave out the extra electrons here for a second so we can see. It does it so fast that we don't even notice a difference. And so both of these structures up here exist, okay? So we have to represent them, but we would call this resonance because it actually alters the structure just a little bit. And so we end up with these like 1.5 bonds with ozone because of the resonance. And it increases its stability, right? And that's something we're going to continue on learning as we go, okay? So that's something called resonance. We're going to work on that a lot more, but that just gives you a little bit of a sense for that, okay? The last little piece that we want to address is that there are exceptions to the octet rule. So I'm just going to throw that at you real quick, just so you know. Exceptions to the octet. Okay. Boron and beryllium can be under the octet. It's because they're so small, they're actually kind of okay with less than 8. Okay? And then everything third row or below can be over the octet. Okay? So beryllium and boron can be under. And then everything third row and below can actually be over. Why is that? Well, remember what happens in the third row. We now have access to the D. So there's this whole other orbital that has space, okay? So anything that's in the third row or below can actually take on more than 8 electrons. And if you're wondering if it will, okay, then what you can look at is the formal charge. Sometimes having more than an octet will actually help the formal charge. Okay, so there's a reasoning for that. A good example, if you want to try on your own, would be the sulfate ion. Sulfate -2. You can give that a shot. We'll talk more about that in class next, the next class. So try that out. See if you can't figure out the expanded octet, but we'll go from there. Okay? Hope that was helpful. Try the practice problems, and